Colligative properties are properties that depend only on the number of solute particles and not the identity of the substance. Your book talks about 3 colligative properties: vapor pressure lowering, boiling point elevation, and freezing point depression. We'll focus on boiling point elevation and freezing point depression. To calculate the boiling point elevation, so to calculate the number of degrees a boiling point of a solvent will increase by adding solute, you need to look up the Kb for the solvent, so that's the molal boiling point constant, and multiply it by the molality of the solution. If you want to calculate the number of degrees that a freezing point will be depressed, that it will go down for a solvent, you need to look up the freezing point constant for that solvent and multiply it by the molality of the solution. If you're dealing with an ionic compound as opposed to a molecular compound that you'll be dissolving in the solvent, there is an additional step. So we'll start with an example of a molecular compound, sugar. If you have 0.500 moles of sugar dissolved in 1 kilogram of water, then you have a 0.500 molal solution. In order to calculate how the boiling point would change by taking the water and adding sugar and making it into a solution, we first need to look up the boiling point constant for water, which is 0.512 degrees Celsius per molal, and we need to multiply it by the molality of the solution. And we find that the boiling point elevation would be 0.256 degrees Celsius. So that means if water normally boils at 100.0 degrees Celsius, and you add enough sugar to make a 0.500 molal solution, then you have a new boiling point of 100.256 degrees Celsius. As I mentioned, it's a little bit different with ionic compounds because it depends on the number of particles of solute that are in the solution. And ionic compounds we know dissociate into their ions. So for example, 1 particle of NaCl dissociates into a sodium ion and a chloride ion. So if we want to calculate the freezing point depression for a solution of NaCl in water, we need to include the number of particles that are produced from 1 particle of NaCl, and so this is often represented by a lowercase I, and then we can multiply that by the freezing constant and the molality of the solution. So for NaCl, every NaCl particle produces 2 ions. We're still talking about our solvent as water, so the freezing point constant for water is 1.86 degrees Celsius per molal. And let's say we have a 0.200 molal solution of NaCl. Then the freezing point would be depressed by 0.744 degrees Celsius. So if the freezing point of water is normally 0.00 degrees Celsius, and we depress it by 0.744 degrees Celsius, then the new freezing point for water is negative 0.744 degrees Celsius. Here's your first practice problem. The molality of an aqueous solution, molecular substance, is 0.500 molal. What is the boiling point elevation? The Kb for water is 0.512 degrees Celsius per molal. If 150.0 grams of ethylene glycol are added to 600.0 grams of water, what is the freezing point depression? What is the new freezing point? Kf for water is 1.86 degrees Celsius per mole, and ethylene glycol is a molecular substance. And your last practice problem. Many people believe that adding salt to water for cooking pasta will increase the boiling point of water and cause the pasta to cook faster. Assume you wanted water to boil at 105 degrees Celsius and you had 1.00 kilograms of water in your pot. How many grams of NaCl would you need to add to the cooking water? Remember, NaCl is an ionic compound.